Hello, welcome. Today we will talk about first law of thermodynamics. First law. Okay? So the first law of thermodynamics is conservation of energy. That is, energy can be neither created nor destroyed. So in equation, that is delta U equals Q plus W. Let's think about a system. Then there is internal energy of that system. So let's say it's 100 joule, and we do some work on it. Work. We push this and we okay, let's think about this kind of system, and this is a lid, and we push this into this kind of oh wait, no, this kind of shape. We push this, the volume of this chamber, this is a chamber, has decreased. So delta V is minus 0. Oh no, delta V is negative, okay? And this is delta L. We pushed it with external force. So we did work on it, positive work, and then the chamber internal energy is going to change. How? Like this. Q equals minus P external delta V. Oh wait, W. Sorry. So how did we derive this? It is very simple. In general physics, work equals F times delta L, external force, right? Which is equals to the area of where is it? This lid, right? This lid is going to look like this in this view, and this lid is going to have area A. So we can change this equation into P external times A times delta L. Then it'll be P external delta V minus. How is that? Delta V is the volume of this empty space. That is how much the volume of this system changed, right? It used to look like this, but now it contracted. So that amount is delta V. And I know that this is quite confusing, right? Why is there a minus? So if you're learning thermodynamics for mechanical engineers, then there is no minus here. But for material scientists, there is a minus. Why? Because our main focus is the system. So when you do a positive work, which is you contract the system and the system's volume is reducing, then you did a positive work. Of course, the system's energy is going to increase because you did work to the system. So if the system's energy is increasing, W has to be positive. And let me write it. If work is positive, in order to achieve this, if there is no minus, then it should be wrote like that, right? But this is positive. This is positive. This is negative because you contracted it. Delta V is V final minus V initial. This is initial. This is final. You can see that final has a smaller volume than initial, so this is negative. So this is negative. Then this has to be minus, right? But if you learn that if you learn mechanical behaviors of materials, you'll learn that external pressure is positive for compressive pressure, or force. It's the same concept, okay? It's just divided by the area, so it's the same concept. It's negative when the pressure is tensile. So you pull the lid. You pull this lid like here in this direction, and the volume increase. This kind of situation, pressure is negative. Okay, so back to this situation. Now, in order to make this plus, you have to add a minus here. Okay, it's just that simple. That's why there's a minus here. So this is the sign convention. Sign convention. Same logic goes for Q, which is heat. If you give heat to the system, let's say you just heat it up. Of course, this internal energy is going to increase. So Q is positive, right? But when the surrounding area has lower energy, like we just put this, let's say this is some kind of stove, and you put it in the freezer, then the heat is going to go from here to here, from system to surrounding. So of course Q is negative. Okay, it's just that simple. So back to this first law, what this law is telling us is that the amount of work and heat done to the system is going to be exactly the same as the change of internal energy. Change of internal energy. Yeah. All right. Now, we will talk about state function vs path. What is state function and what is path function? State function is the property of the system. Of system. Example is temperature or pressure. So if there is this system, T equals 298 Kelvin, and the temperature drops to 98 Kelvin, then delta T is equal T2 minus T1, which is minus 200 Kelvin. Okay? How do you define state function? Definition. So if a certain quantity, let's use T, from T1 to T2 equals T2 minus T1, then it is state function, right? So let's say let's say there's this system. Back to this case. Back to this case. So state 2 is 98 Kelvin. State 1 is 298 Kelvin. If you want to calculate the temperature change, you don't have to do this. You don't have to integrate over a certain time or period. All you need to do is just simply minus. Subtract from state 2, and you will just get the temperature change. It's just that simple. But when it comes to path function, this is when things get tricky. So let's say there is this piston. This is lid. Back to this example again. So when we push it, we use external pressure. Then when we plot this curve, PV curve, it is going to be like this. V1, V2. So if you we call this isobaric, and we call this, wait, I forgot the name of it, sorry. Isotropic. No. Same volume, isovolumic. So what we are doing in one is we are expanding this piston from V1 to V2, and delta V equals V2 minus V1 is going to be positive value, so the work done is going to be minus P delta V external, which is minus P1 V2 minus P V1, and P1 is plus P2 minus V2 minus V1 is also plus, so this is negative work. Negative work is done. And from this equation, you can clearly see that 2 isovolumic change, you don't do any work to the system because this part is going to be 0, right? It's the same, V2 and V2. It's the same. So here, work is 0. So if you move from point 1 to point 2, wait. If you want, you just have to plus, right? Then work is going to be minus P1, V1, V2 minus V1. Okay? Let me just move this to here. Now let's look at case 2. Case 2, 3, and 4. Let's look at this route. Then, as before, this part work is going to be 0. This part we have to calculate. So work equals minus P V2 minus V1 is going to be, we use this pressure, right? So minus P2 V2 minus V1. So this is route 3, 4. As calculated from before, this route 1, 2 is minus P1, V2 minus V1 is different, right? So this is conclusion. Work is a path function. If you take different routes, you'll have different work. So if you express this in equation, it's like this. Right? So even this is a very weird expression because you can't really define, you can't define, let me use this. You can't define the work of a particular system, right? There is no work of system. There is temperature of system, there is pressure of a system, but there is no work or heat of a system. You give work to system, or system does, like, gives work to surrounding. There is no work or heat of system, right? This is just like, it's a process term. Process, it's part of a process. You give work to system. It's not the work, it doesn't belong to system. That's the path function. That's the clear difference of path function and state function. For state function, it is a state of that system, like your name, or temperature, or pressure, your height. Yeah, all of these are states. Okay? So this is just a very simple way of expressing path function. If you integrate it from work 1, you integrate from here to here, it is not going to be work 2 minus work 1, because here and here is different. If you take various routes, it's going to give various value. Okay? So this is path function. Now, why are we talking about this? Why are we talking about state function and path function? It is because we are talking about the first law, U and equals Q plus W, right? We're talking about this, and we just concluded that work and heat are both state function, path function. Internal energy is a state function, right? This is why we are talking about it. So the problem is with path function, it is mathematically very unstable. We can't easily use this for engineering or for science, whatever. Like we can't accurately, like freely play with it as we do state function. Why? Because as we see from this this equation, that if we want to calculate what's the change, we can just simply minus. We know this, it's like a name or a property of the system, so we can easily manipulate this kind of state function. But this kind of path function, we need to know exactly what kind of route it took, right? We need to know specifically it can be some kind of different route like this or like this or like this. We have to think about all this kind of different cases, which is very inefficient. So our strategy is to change this kind of path function into state function. This is our main strategy. Okay? So, uh, so um, before we keep moving on, I have to tell you that the basic notation of path function and state function. So for state function, you use du, okay? And for path function, you use this kind of signal, which is maybe, I think it's delta. So delta Q plus delta W. Du is like infinitesimal change of internal energy, and del Q is the infinitesimal change of heat. Like it gives heat or it gains heat, right? And you use this kind of signal because Q is a path function. And U is du because it's a state function. I hope you use this very clearly and don't mix them up because it's a very important and distinct concept. Also, some professors like to use like this kind of equation or like this kind of equation, right? Or even like this for simplicity, but here they're all wrong. Okay, like these are all wrong way to write it. The only correct way to write it is this or this. Only these two ways. Because you can think about it. It's very simple. So you can't have a delta Q, right? Because Q already has a meaning of delta. You give Q to a system, right? There is no Q of system. You give Q. This is already a delta term. So you don't need another delta here. You don't need that. Same logic for work. So this is not infinitesimal change. It's a big change. So it's delta U. Here it's infinitesimal change, infinitesimal case. And we use this delta here for path function again. Okay, all right. Good. Now, what we're gonna do is, let's see. All right, so before I mentioned that I forgot to clarify why internal energy is state function and Q and W are path functions. So I'm gonna do that now. So basically, all the energies, like you, later on, we're gonna talk about Gibbs free energy and something like Helmholtz free energy or enthalpy. These are all state function. You can just easily think about it like, what's your temperature, right? Like you can ask this kind of question, right, for state function. Same thing applies for this kind of energy. What's the energy of the system? What's the energy that the system is currently having, right? So from you may recall this kind of graph from like from from chemistry, chemical reaction, where there is enthalpy change. Then when delta H is positive, it's a endothermic reaction, right? And delta H equals H2 minus H1, which is, this is product, this is reactant. So let's say there's this kind of equation. No, wait, sorry. Then HC minus HA plus HB is delta H. If this is positive, then it's endothermic. If this is negative, this is exothermic reaction. Anyway, you can clearly see this from this kind of examples that um, these wait energies are state functions, and you may question something like, what's the difference between these energies? And later on I'll explain much deeper, but at this point you can just think of them as all man-made um, energy for different situation. Like you can use this for certain situation, you can use Gibbs free energy for certain situation. It depends, and it's not like something that is absolute. You can just remember that term. It's not absolute. Energies are always relative. It's never absolute. You can never say it has absolute energy. But now you don't, you might, it's normal that you don't understand. I'll definitely come back to this. Anyway, so energy and some entropy or mass or temperature, pressure, these are all state function. Path function is like what we talked about here, is something that depends on what kind of path you choose. So how you do it, how you give heat or do work to the system, it depends on specific route. Okay, so that's why Q and W, they are path function, and U is state function. And now our strategy is going to uh, turn these two into state function, so we can easily manipulate it, like I said. But before doing that, we'll uh, we'll talk about some detailed examples, and we want to think about this first law more in a detailed way. Okay? So now, so when we talk about system, it's just simply the target that we want to examine. Okay? It can be a material, it can be a portion of the pipe, or it can be anything, okay? It can be a car, it can be anything you want to examine. And surrounding is simply the surrounding of the system, okay? These are all surrounding. And system and surrounding makes up a universe. Simple, right? Of course. So, there are two types of system, open and closed. Open is material enters or leave the sys. Okay? Closed, no, nothing enters or nothing leaves. So let's say there's this pipe. When we talk about this specific portion of the pipe, this is a pipe. This is our system. Not here, not here or here, only here, okay? These blue parts are all surrounding. All right. Now, fluid is gonna come in this system. Is this open or closed? Well, of course it's open system, because it's very simple, right? And when we think about if this fluid is running like this, right? This is now is not a portion of the pipe. The system is portion of the fluid, this specific part of the fluid, and it's moving. Now, is this open or closed? Why don't you guys all think about it? Of course, it's closed, because this fluid is moving. This fluid is also moving. They're moving at the same velocity. So when you think about this portion, then nothing comes in nor leaves. This part is moving. So it's a moving closed system. Closed system. All right. So that's it for open and closed. Now we will talk about let's see. We will talk about heat engine. Heat engine. We'll go back to this kind of diagram. P2, P1, V1, V2. Now, heat engine. We will do a counterclock rotation. Okay, so work 1 to 2 is, as we talked about, we can integrate this like this, V1, V2. You can see how we got this, right? Because as we talked about before, the delta W minus this delta signal minded equals minus PdV, right? External. And we simply integrated. So W I told you that there is already a delta meaning inside, so you don't need this delta here. Okay? And you integrate this equal w1 from w2 equals minus p dv v1 v2. This is how you got this. Okay? Now, from 1 to 2, 1 to 2, right, is going to be w1 to 2 is going to be w1 to 2 is minus p1 2 minus v1. Simple integration. Okay? And from the 2, this thing, as we talked about, delta v is 0, so work is 0. So 1 and 2 is this, right? W minus p1 v2 minus v1. And this C3, it's W 1, 2, 3, 4. Okay? Point. This is point. That's these 4 points. Now 3 to 4 is minus P dV. P is P2 now, right? Because we're here now. So V2, right? From V2 to V1. So it's going to be minus P2, V1 minus V2. And 4 is, of course, 0. So if you add all 4 of them, if you do a counterclockwise rotation, then total work is going to be minus P1, V2 minus V1, minus P2, V1 minus V2, which is going to be minus, so you get that out, then P2 minus P1. So it's positive work because P2 bigger than P1, V2 is bigger than V1. Now if we do a clockwise rotation, then all these signal is going to be opposite, obviously, because when we think about from 4 to 3, it's going to be minus P2, V2 minus V1. It's opposite from this. Same logic for 1 to 2. So the total work is going to be P1 minus P2, V2 minus V1 is smaller than 0. So this is clockwise rotation, right? Then for heat engine, you need to do work to the surrounding, right? So what kind of rotation would you use for heat engine? Let's say these two diagrams can be one of the like this kind of rotation or this kind of rotation. Either of them can be used for heat engine. Then what kind of rotation would you choose? Then when you think about it, the purpose of heat engine is to do work to the system, right? So let's say there's a train, there's a heat engine. Then this heat engine is pushing this train forward, so it's doing positive work to the surrounding. So system is doing work to the surrounding. And we talked about this. When system does work to surrounding, it's obviously losing energy. It's converting its internal energy into the positive work. So its internal energy is dropping, right? So, of course, the W has to be minus. W is a negative term. So if you see this, it's clear, right? You have to choose this. You don't have to memorize this, but you have to learn how to think in a logical way like this. This is heat engine. Okay? Yeah. So much for lecture one. No, wait. Lecture for first law. Next lecture we are going to talk more about detailed examples and some other terminologies, and that's all. Thank you.